Hi, this video is going to be a very interesting one. We will totally understand why a charged comb attracts paper bits. First off, let's revise what we did with torques. Here I have that gate, okay, that's the rotation axis, and here's the gate, and here's my line of application of force, okay, and here is the perpendicular distance between the rotation axis and the line of action of force. Let's call it lever arm L, okay. Then I say that torque is equal to the magnitude of force times, or simply multiply uh, it with the lever arm, which is the distance between the rotation axis and the line of application of force, okay. So this is torque. Now, first off, we consider the force on an electric dipole in a uniform external electric field. What that means is that electric dipole is a combination of two charges, equal and opposite charges. Suppose this is plus q, then we would have minus q, and we call the combination of these two an electric dipole. Okay, and since these are opposite charges, they would be attracted to each other like this. Okay, so consider a dipole separated by a distance d and an electric field E like this. It's uniform, it's equally spaced here, 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 and so on. Okay, and consider this positive charge. What's the force on this positive charge? We had earlier seen that electric field was defined as force per unit charge. It was defined as force per unit charge. Therefore, if electric field is force by charge, the force would be field times charge. This is what it is: field E times charge, and the direction of E is same as the direction of force since it is a positive charge. Where when the charge is negative, you have minus q, so it actually reverses the direction of the force. So actually it's in this direction. It The force on the negative charge is opposite to the field. Okay, that much is clear. Now since they are attracted to each other, imagine them to be connected by some kind of rod. Okay, imagine them to be connected by a rod of length d is the distance between them. Okay, then the as you can see that the force on this top is like this and force on this top is like that. So both forces are trying to rotate it like this, okay, like this actually, and then the force would stop. But if it has gained some enough momentum, it would continue and so on, but that's not what we want here. It will actually tend. So we can see that the forces, uh, this one and this one, are trying to align the dipole with the electric field. I hope it's clearly visible. Now let's do a small calculation of the torque. Okay, suppose this angle is phi, then this is clearly d sine phi, because sine phi is perpendicular divided by hypotenuse. If we do d sine phi by d, we will get sine phi, which is correct. Okay, so this is d sine phi, and the center of this would be the midpoint. The midpoint of this would be the center of rotation, and therefore the axis of rotation would be like this coming out. Okay, I hope that's clear. Then the magnitude of force here is QE, and the lever arm is actually d sine phi divide by 2 because the axis is between these two like this. I hope that's clear. Okay, so since both of these torques, one from here and one from here, tend to rotate it in the same direction, the two torques add up. So we have QE d sine phi by 2 plus QE d sine phi by 2. So as a total we get 2 QED sine phi by 2, which is QED sine phi. So this is the torque. And again I emphasize that the force on the positive charge tends to rotate it like this, and the force on the negative charge tends to rotate it like that. And as a result, the dipole tends to align like this, with the positive in the direction of the field and the negative away from the field. Okay. Now, some molecules like H2O and N2O have equal amounts of positive and negative charges like in a dipole, but excess positive charge is concentrated on one side of the molecule and excess negative charge on the other, and these are called polar molecules. Since the charges are kind of separated and they are equal, they behave like a dipole and are called polar molecules. When the external electric field is absent, they are aligned randomly, like the minus is on the top here, plus is on the top here, like random. But when the E field is present, uh, these dipoles tend to align like we saw here, plus in the direction of E and minus away from it. So it will align kind of like this, plus here, negative away, plus in the direction of E, negative away. But it won't be quite perfect since there are thermal agitations in the material, which means that the molecules also move due to their translational kinetic energy due to temperature. Forget that, it doesn't matter. But even non-polar molecules can become polar due to electric field, because it pushes positive charge in the field's direction and the negative charge opposite in the opposite direction. Okay. Now, since the E field is like this, therefore a negatively charged object must be the cause of it. Let's assume it is, and if we place a negatively charged rod here, and this is maybe any material which we wish to get attracted to it, say it's the molecules of a paper bit, then we see that the plus positive charge is actually closer to the negative charge than the negative part of this. Therefore the attraction dominates. Positive and negative attract, and though the negative and negative also repel, but since it's farther away, and by the Coulomb's law it's inversely proportional to the distance. As the distance increases, the force decreases. So repulsion is lesser than the attraction, and as a result the paper bit gets attracted. That's it. I hope it makes sense, and thank you. Here Here is some more content. If you find it interesting, I'll make a video on it too. Have a look. Here are some questions. If you want, I will explain these too, but try them yourself first. Okay, that's it. In the next video, I will begin magnetism. Please watch till the end of the series. Thank you.